Hello, today we're going to explore the concept of a confidence interval and how it relates to everything that we've been learning so far. So far we have looked at situations where we have known population parameters in addition to knowing various sample statistics. And we first saw how we could use z-scores to determine the probability of getting a value of a certain size based upon knowing the population mean and standard deviation. And then later we saw how we could apply the central limit theorem and then look at sampling distributions and using standard error to see about getting a mean of a certain size. Now, all of this is all well and good if you know the population parameters. However, most of the time we will be unaware of those population parameters. And so trying to do statistics, or at least the stuff that we've learned, will be very limited in our application. However, we can take some of these concepts that we have learned and we can apply them to situations, and we can still get useful information by looking at the sample statistics. Now, just as a little review, we have the standard error, or SE, and we found that by looking at the standard deviation for a population divided by the square root of n. And we saw that with a sample, I showed you, that we could still calculate standard error, but instead of using the population standard deviation, we used the sample standard deviation, and we still divided by the square root of n, or our sample size. And with this, we can calculate a standard error for our sampling distribution, or at least we can estimate it. Now, we also saw that when we have population, which I want to represent by this circle with a P, and we draw samples from that population, those samples vary because they should be, for the most part, composed of different people. And those different people, they're going to have different attributes. So even though we would expect our population or population mean, or mu, to be roughly equal to our sample means, it is not always the case that it is exactly the same, because there is variation. We did see that if we look at the frequency distribution of samples drawn from a population, we'd end up with something approximating the normal distribution. And we'd have a mean that was equal to our population parameters, and then we had various things such as 68% of the scores would be within plus or minus 1 standard errors from the mean. So this is what we have done so far. But now we have a situation where we don't know mu. So we cross that out. We still know that 68% of the scores are within 1 standard deviation away from the mean, and that about 95% of the scores are within about 2 standard deviations of the mean, and that 99.7% of the scores are within 3 standard deviations of the mean. That has not changed. But now we don't know where our mean is, our population mean. So we don't really know the properties of the sampling distribution. So what we're left with, when we look at a sample, so we have a sample, and we have a mean of x bar, and we have a standard error. Now, we know that the standard error represents a standardized unit of measurement among that sampling distribution. So instead of trying to figure out exactly where mu is, or our sampling, or our mean for our sampling distribution, what we can do instead is we can try to calculate a range for where our mean lies. Now, you might recall that a z-score has a percentage associated with it. And so using that information, we can then use this to build a confidence interval. And so basically, if we go back and we look at this formula, so z equals the sample mean minus the population mean over the standard error. If we did some math and did some simple algebra to rearrange this equation, we could start by multiplying by the standard error, and so we'd end up with z times SE equals mu, or the mean minus mu, and then to cancel out the negative, we'd end up with the mean minus the z-score associated with that mean times the standard error is going to be equal to mu. Alright, now we don't know the z-score associated with that mean because we don't know mu. So we don't really know that stuff. But what I can do is I can create a confidence interval. And so I can go in and I can look at my z-table and I can get out certain percentages. So knowing about what I do about the sampling distribution, I know that my sample mean is likely to be close to my population. I just don't know how close because of the fact that sample means are normally distributed in a sampling distribution. So what I can do then is I can, for a given z, and the standard that we use is the 95th percentile, which gives us a z with the 95th percentile, essentially plus or minus 1.96. And so, sort of putting that together, now I don't know my mu, and I don't know because I don't know mu, I don't know how many standard error units my mean is away from there, but at least I can try to figure it out. And so, knowing that the mean should be close, or is more likely to be close than it is to be far away, I can create this confidence interval. And so basically, that confidence interval, I would have my sample mean, and then I'd do plus or minus z times the standard error. And of course, the standard z that we use is going to be the 1.96. So what we're left with is our mean plus or minus 1.96 times the standard error. And what this will do is this will create a 95% confidence interval around the mean. And so basically what that translates into is that I don't know what the true mean is, but I am 95% confident that the mean exists inside of this range. And so let's just put some numbers in here, and I'm just going to make up some numbers. So let's assume that my mean is going to be equal to 100, just to try to keep things simple. And my standard error is going to be equal to 10. So using that equation for the confidence interval, which I'm just going to call Ci, I'm going to end up with 100 plus or minus 1.96 times 10. And so my confidence interval would then be 100 plus or minus 19.6, and therefore it would be about 80.4 to 119.6. Now that's just sort of the basic calculation. So essentially what that means by creating this 95% confidence interval is that 95% of the time, or 95 times out of 100 the true mean, or population mean, would be would fall in that range. And so in other words, I'm 95% confident. Now, just like some terminology that goes along with these confidence interval, the upper limit this is going to be the largest value, and then we have the lower limit. In our example, the upper limit was going to be the 119.6, and the lower limit was going to be 80.4. And so that sets the range where we would expect 95 times out of 100 that the true mean would exist somewhere inside of that range. Now, of course, this is just a nice way of estimating things. And we can see this applied to a number of situations. And so, for instance, if we were to conduct a survey, we wanted to find out the attitudes that people had. We could go and we can do the survey, and you've probably seen results along these lines where they'll say that 50% of the population agree with a certain position, plus or minus 2%, or with a margin of error of 2%. And so essentially what they're saying is that somewhere that on the sample that they had, that 50% of people agreed, but that the true population mean should be somewhere between 48 and 52%. This is the application, or the most basic application, I should say, of this idea of a confidence interval.